Hi pre-calc, hope everything is going okay. Prior to this video, I did a short, like 5-minute how to graph in 3 dimensions. It has a worksheet of just 3-dimensional graphing and the solutions are up. So I'm going to do 2 examples here, but if you need a little more help with drawing in 3D, you could look at that short little video. It is linked up on our distance learning calendar as well, and the handouts are in the locker and in the solutions. So everything we're doing today is exactly stuff you've already done, but now we're going to do everything with a 3rd dimension. All right, so the way a 3rd dimension works is we're taking the XY coordinate system that we're used to, and that's going to become like the floor. So that's 2-dimensional. Think of it like that's the area of the floor. To add that 3rd dimension of height, we add a Z axis, which goes up. So that's what gives us that 3rd dimension. And so if you're going to graph and you want it to look like a 3-dimensional graph, that's why the XY is sort of at an angle. So if I'm going to graph the point 3, 2, 4, so it is an X, Y, Z coordinate system. That tells me I would go out 3, 1, 2, 3. So that would take me out this distance. Then I would go over 2 in the Y direction. I sort of lost my lines. So going over 2 would take me over in this direction. So X and Y are really easy to do. It's the Z direction that's a little bit harder, because if we're going to do the path, 3 in the X, 2 in the Y, 4 in the Z, what you want to realize is 1, 2, this is the height of 4. But we're doing it from here, because remember, everything is tilted to give it that 3rd dimension. So I'm going to take this particular height and I'm going to do it from this point down here, and I want it to be about the same height. So I'm going to do it about that high. That point where I ended would represent the, like when you're doing a vector, that would be your final position. If I was doing a position vector, I'd go back to the beginning, the origin, and draw a vector out to that point. I'm going to hold off on that for a second, because what you want to always show is the related prism that goes with that point. So by doing that path, I've done the length, the width, and the height. We want to fill out the prism so that we can then see everything that your final vector is basically going to be a diagonal that goes through that. So I always like to finish off the floor, and then we have to do all these heights. So the 2 that are coming from the back will be the same height, and these 2 in the front will be the same height. So I left our original path sort of in the orange. That was the 3, 2, 4. Then we fill off by making this prism, so now I can connect all my edges, and the actual position vector starts at the origin and goes to that final point, preferably straight. There we go. That is graphing in 3 dimensions. So let's try another one. Here we have 4, -3, 5. Remember, this is your X, this is your Y, this is your Z. So now I'm going to come out 4. So 1, 2, 3, 4. So you come out 4 in the X direction. We're going to go back 3. So here's the equivalent of 3. So we come over here and then up 5. So 1, 2, 3, 4, 5. So this again is that distance, and what I'm going to do is try and match that same distance going up. It won't be as high because everything is tilted forward to give it that 3-dimensional look. But before we draw our vector, I'm going to finish off the prism. So you can kind of see the floor here. We have this back that goes up to 5. And this other backing will go up the same height because they both sit in the back. The 2 front heights will be the same because they're sitting in the front. And then we connect the vertices It's not always the easiest thing to do these, I totally get that. And your position vector starts from the beginning, and it's basically the diagonal that goes through the prism. All right, and that would be the position vector that goes with a point 4, -3, 5. So let's take a look at some stuff that we've already done and look at it three-dimensionally. So now your vectors in their component parts, last time we saw the x and the y as scalars of your unit vector I and j. Now we include a z scalar to go with a k, so it's ijk. I is used to denote a unit vector in the x direction. That's your horizontal movement. J represents in the y direction. K represents in the z direction. And you can see those. So this is your x, this is your y, this is your z, xi, yj, zk. And that would give you your vectors that you could place wherever. In this case, x, y, and z are 1 because those are still unit vectors. All right, we can find the distance between 2 points in 2 dimensions. You can also find it in 3 dimensions. It's really still just Pythagorean theorem. If you're finding the magnitude, you're just adding another dimension to your Pythagorean theorem. So remember we talked in the last time about displacement vectors. Displacement vectors is from head to head, the position between the heads of 2 vectors. And if I have a displacement vector, this reads from A to B, from the head of A to the head of B. Remember, we always do it backwards algebraically. And then to find the magnitude of that, you're going to, whatever that resultant displacement vector is, do a Pythagorean theorem of it. Okay, so let's look at what we had up here. So we had a vector A up above that went to the point 3, 2, 4, and we had a vector B that went to the point 4, -3, 5. That's from the very first problems. And they want us to find the vector from the head of A to the head of B, which will be vector B minus vector A. So again, remember when you subtract, you're subtracting like the I variables, the j variables, the z like positions. So the first one will be 4 minus 3, and then we have -3 minus 2, and then we have 5 minus 4, so nice friendly numbers. So that would be our displacement vector. That goes from A to B, from the head of A to the head of B. Now if we want to find the magnitude of this vector, we do Pythagorean theorem in 3 degrees. 1 squared plus 5 squared. You don't need the negative because you're going to square it. So that's 25, 26, 27. It's going to be the square root of 27, which we could simplify to 3 rad 3, or we could get a decimal. Don't really care. Yeah, that's it. Finding the distance. So it's just adding another dimension. So again, position vectors come out of the origin and they go to a particular point. Displacement vectors typically they could start at the origin, but it's not really necessary. It's just, you know, the distance between the head of 2 vectors. So to continue, it says find the displacement vector from the point 8, 2, 1 to the point 3, 10, 4, and then find the displacement vector. Oh, in other words, find that displacement vector. I was like, why is it saying exactly the same thing again? All right, in shorthand, this is what we're doing. Okay, so we know that if we want to find AB, I always find it helpful just to write it down because it slows you down and it reminds you got to do the opposite. So it's going to be B minus A. So the displacement vector will be 3 minus 8. You know, I'm going to write it out just so people know where my numbers are coming from. then 10 minus 2, and then 4 minus 1. So that's going to give me negative 5, 8, 3. That is the displacement vector. The magnitude of that displacement vector is Pythagorean theorem. So 5 squared plus 8 squared plus 3 squared. So that's going to be 25 plus 64 plus 9, which will be the square root of 98, which is 49 times 2. So that simplifies to 7 rad 2. Okay, that was that. Now find the position vector to the point that is 70% of the way from point A, a new point A, to a new point B. All right, so that means in writing what we are doing, remember when you're finding the position vector to something that is part of the way, I'm going to kind of do a really rough sketch of this just to remind you what we are doing. So if I was doing 8 to 13, that would be somewhere here. So let's say that's A. B would be somewhere at 3, 10, 4. So B would be somewhere over here. Here's B. Here's A. The position vector from A to B is this vector. So that is the vector from A to B. And what we are looking for is the position vector that is 70% of the way. So something that's coming out to here. So remember, this involves a path. The path that we are taking is going to look like this. Let's see if I can pull this. We're going to go out through A and then add to that 70% of AB, and that will then give us our resultant vector. So as what we are doing is we're taking A plus 70% of the vector that goes from A to B, which is another way of saying we're taking vector A and adding it 70% of the vector that is represented by B minus A. So that's what we're actually calculating. So this is 8 to 13. That is getting added to 70% of, I made a little mistake here, this should be a vector. The vector B minus A, so 3 minus 8 is a negative 5, 10 minus 2 is 8, 4 minus 13 is a negative 9, and so we have 8 to 13. I'm going to distribute that 70% to everything, so that's going to give me a negative 3.5 and a positive 5.6 and a negative 6.3. So you're multiplying everything by 7 with one decimal place. And now we add the two together. So 8 minus 3.5 is 4.5. 2 plus 5.6 is 7.6. 13 minus 6.3, that's going to be 8.7. And that is going to be our displacement. Actually, I'm sorry. I just had a moment there. This is our position vector because it is coming out of the origin. So it is the position vector that takes you 70% of the way along the vector from A to B. And that's really, it's nothing new. It's really just adding on another layer, another dimension to what we've been doing.